So today we are talking about the pre-production pilot runs, specifically for plastic injection molding. Why it's so important, and what kind of things do we actually look at when trialing a mold, and how does it typically get done, and so on and so forth. And finally, what are the key parameters in this process that we sort of tweak to get to the optimal parameters that get us the best results.
You're listening to China Manufacturing Decoded from the Sofeast Group.
Plastic injection molding is a very common, very widespread process. It's made in truly industrial scales in China, especially around, let's say, the Shenzhen and Dongguan area and the Ningbo area, but it's all over the place. And when we walk around our Dongguan facility, we walk around Agilian, here and there we see some plastic injection molding shops. I mean, it's really that common. And obviously, we opened our own plastic workshop last year, so we're getting deeper and deeper into this process. And today, I am with Paul Adams, our senior engineer. Hello, how are you doing?
Oh, Renaud, yeah, good to be back. And so it's a great little topic. I love this one.
Right. Paul has a wealth of experience in this process, and we're going to break it down. And so the first question is, why is it so important, right? We always say every time you have some custom designed components, they're going to be made for the first time. You got to do a pre-production pilot run. That's like a general rule, right? And then you also do the same for assembly, testing, packing, everything. Basically, you test everything that's going to be done for the first time, because that's the reason to that's the way to validate, right? The objective is to validate that the process is ready. But in the case of plastic injection molding, I mean, what are the kinds of typical issues that happen when someone goes in right away? Okay, made a mold, and like let's go ahead and let's make a bunch of parts right away, right? Why is it so important?
Well, if you take a step back, and so a lot of customers are very, very keen to get their product up and running as soon as possible. Therefore, they're very, keen to get parts out of the mold ASAP. And we're under always a lot of pressure to potentially skip certain processes and steps. And the pilot run is a super important one that we will not, we will push back on that. So no, you can't afford to skip that, because during that pilot run, we're able to identify, some of the main issues that you will see with a non-optimized injection mold machine, or the mold itself. For example, you'll see a lot of flash. Okay, some people, flash is not a problem, because it can be trimmed off, but that's just an indication that everything's, it's not optimized, or there's an issue somewhere that needs to be addressed. And other things like the efficiency of running the machine, and the man hours and everything like this, that can be optimized. And without the pilot run, we've got no chance of addressing any of these issues, or applying any of the optimization that we can actually look at. And another thing that we can certainly gain is having a baseline or a benchmark with respect to what quality is all about. Now, if we've optimized everything through a pilot run, we can set that benchmark with respect, okay, this is the optimum cycle time for a product or a component coming out of the machine. This is the acceptable quality level from a dimensional point of view, color point of view, and all of the other aspects that come with sort of general injection molding issues. So it's really important that we push back, and we will insist on doing these pilot runs with one, looking at optimizing the design of the mold tool itself, but two, sometimes just as importantly, is optimizing the machine settings itself, as in the injection mold machine or the press.
Right, right. Yeah, and we'll get back to that. And again, let's take a step back and think, okay, what are the steps, right? Because people might be wondering, okay, wait, how does all of this come into play? So first, the design of, let's say, the plastic part. So whatever, a part of an enclosure or maybe some kind of internal part, maybe mechanical parts like gears and things like that, right? It gets designed. There's CAD drawings, and that gets hopefully reviewed and confirmed and everything. Okay, then the tooling itself, the mold is designed. Okay, in principle, actually, when you design the part itself that goes into the product, you also have in mind the design of the tooling, right? You want to make sure it's designed as fit for manufacturing. Okay, then someone actually designs the mold and the cavity, the core, maybe the side actions and things like that, where the gate's going to be and so on. And then they do the fabrication, right? They get the block of steel and they carve the cavities and so on and so forth. And that takes a few weeks. And then after that is like, ta-da, okay, it's ready to be trialed. And there's specific steps here. Like you would never want to go into mass production right there. Oh, okay, we have 10,000 pieces, of it to make. Like it's so urgent. Just make them and then we'll see after. If there's a bit of flash, we'll just trim, that's extra labor or whatever. If it's a bit burned, a bit whatever, just adjust along the way. Like we trust the guys and just do it. Nobody would do that, right? There's certain steps that they would follow at that stage, right?
Well, yeah, there's certainly a number of steps that sort of look at. You talked about optimization from the CAD to the actual block of steel being cut. We go through a process of DFM, design for manufacturing, a review, and that's a very serious thing. And we work collaboratively as a team between our designers, the customer, if it's their product, and our injection mold tool designers. So that's a really important step that we follow. But the moving on from cutting the steel and putting that into the machine to start with, that's the first stage of trialing a mold tool. Now that could actually take about 30 days. And everyone, when we say 30 days, everyone said, yeah, excellent. I'm going to get my products in 30 days. Well, no, that's not particularly the case, because during this initial trial, we will not have the specific finishing. For example, if you need a particular texture, which we've talked about in a separate podcast and you can read about, but that won't include any of that. So basically what we're trying to do here is run the tool to see how we have designed it or how it has been designed and make sure that functions as per intended. So you mentioned the sliders, lifters and everything like that. Everything needs a particular timing with respect to when they come in, when they come out, making sure the ejection system is working as well as the injection is smooth, making sure that we've got a full cavity, for example, super important. Nobody wants short shots or part completed components coming out of the mold tool. If we've got multi-cavities, for example, you want to make sure that each of the cavities is completely full and one of them doesn't have excess flash and the other one has not enough material injected into it. So this 30-day period, this initial trial, is to make sure that the system is functioning as intended. Okay, so that's the first in the process of it.
Right. And in the automotive industry, in the consumer electronics industry and so on, they all call it T0, T1, T2 is the first trials, right? It's the first time you trial the mold, the parts are probably going to be a little bit on the small side, right? In most cases, you need to go into a second trial, at least a second one, and maybe even a third one. You'd be lucky to be to have everything approved on the first trial, right? Because they want to be metal safe. That's what they call it, right?
I
The
was
tool
just about to say
designers.
that. Yeah, yeah.
Maybe
Yeah.
you can explain what that means.
Yeah.
Yeah.
Well, when we talk about metal safe, that's a really good, an important point to bring up, Renaud. When we're talking about metal safe, you talked about, the parts being small. You've got to remember that this is it's not an additive process like sort of 3D printing. This is a reverse
Mm.
from that. So we need to take material off the tool in order to make the part bigger. So to be on the safe side, we need to make sure that everything is coming out under tolerance. In other words, if everything needs to be adjusted slightly, we can still machine out components, or in other words, take material off of the tool or the cavity in order to bring the parts back into tolerance or into acceptable tolerance. So that's what we're talking about metal safe. So that's a good point.
Mm.
This is
Yes.
exactly what, you talked about T1, T2, T0 is what we're talking about here. The very first trial where parts are not really acceptable, from a sign-off point of view. Like we said before, they may be out of tolerance. They may be slightly small. They certainly won't have any of the fine texturing that would be specified on certain surfaces. So T0 is what we're talking about here.
Yes, exactly. So that's T0, and the parts are evaluated for the size, right? The dimensions and the aesthetics mostly. And again, this is before any texture, right? And if the dimensions, there's usually a little bit of adjustment here and there, and maybe the aesthetics, maybe okay, then it goes into the next trial. And then, yeah, at one point where it makes sense, they do add the texture, so it's an extra process. And we can link to a nice in-depth explanation of this that you wrote in an article. But it's kind of a long topic, and without any visuals, it's a bit dry. So let's not go into that. But the texture is basically what gives a plastic part is the finish, right? The finish, to avoid that kind of cheap, glossy plastic look, but also sometimes to make it easier to grip. I mean, there's a lot of reasons to add texture on some parts, and maybe not everywhere. Maybe on the outside of the part, maybe on a part of the body, and so on. Okay, so let's say that we get through T0, T1, maybe T2, and okay, this component made in plastic is approved dimensionally, aesthetically. It's all right. We know it's the right polymers and so on and so forth. Okay, done. Approved. Is that okay? Are we okay to go into a batch of 5,000 pieces, 10,000 pieces? Or is there one more step here? Or maybe more than one step?
Well, we've got to break it down from two different angles, or two sides of the fence, let's say. We've been talking basically about the customer side of it, where the customer has the product in hand and they review it against their specification drawing, for example, or the CAD file, or some other reference point. And they will make the mind up with respect to whether that product is correct and acceptable or not, which we will obviously work on the mold tool in order to optimize and bring that product into specification and meet all of the criteria. So we are providing the product for the customer to sign off. So that's one side of the fence. And let's have a look at the other side of the fence, which is like processing from our point of view, from the machining point of view, from the process aspect. So even though the mold tool itself has been carefully machined, polished, textured, and all of the gates have been optimized and everything like this, that's all good. But we still need to make sure that our cycle times have been optimized, the machine has been optimized, and the tool itself is running to the point where it is optimized for maximum life expectancy. Okay. So,
Right.
you've got to look at it at 2 points or two sides of the fence,
Yep.
let's say. So we've optimized the part in order for the customer to say, this is great, this is perfect, let's go. Let's pull the trigger, and here's my first order for a batch of 5,000, 10,000, whatever the case may be.
Right.
We need to make sure as well that we are ready from a process point of view.
Yeah.
So from a tooling point of view, it's not just about the core and cavity. In other words, it's not about the component details of the plastic part itself. It's all about how that tool works. So we stick with the tool at the moment. We'll move on to the machine in a minute. Move on to the press in a minute. But from a tooling point of view, we need to make sure that we've optimized the gate. Now, the gate is where the material, the molten polymer, comes from the sprue into the part itself. Now, that needs to be optimized in order to make sure that we're getting the correct fill of the cavity, as well as leaving, if it's an important aspect, a minimum witness mark where that injection point is on the part itself. So that's something to think about. We're also looking at heating, cooling, heating effect. So polymer reacts to heat. Obviously, it needs to be in a fluid form in order to come from the machine into the tool itself, and that needs to be maintained at a correct temperature throughout the injection cycle, and then cooled at a relevant rate. Not too quickly, otherwise we're going to get shrinkage and warping and sink marks, but it needs to be cooled correctly. So this is a very, very delicate, fine balancing, a very skillful aspect with respect to setting up the machines and making sure that tooling is correct.
Right. That makes sense. Yeah. Anything else that you would typically work on when trialing the whole process?
Well, like I say, I'm just going to stick with the sort of the tool for the moment before we move over to the press. So assuming that we've actually injected enough molten material into the tool itself, we've ensured that we're not getting any short shots. We've ensured that we're not getting any flash. Now, the flash can be there because of a number of reasons. One, you've got too much pressure coming in to the actual tool itself. And that can be optimized by dialing back the amount of injection pressure, but we need to optimize the size of the machine as well. I'm crossing over the barrier a little bit here to machines. It's all about the clamping force. Now, the clamping force will determine the size of the tool that can go into the machine, and that determines how big the machine itself is. But that's another key important aspect we need to look at. I want to talk about cooling for a little bit. The cooling of the injected molten polymer into the tool needs to be cooled at a key rate or a certain rate. It can't be too quick, like I said earlier. Otherwise, you're going to get shrinkage and warpage and some nasty out of shape parts going on. It needs to be cooled within time. If it lasts too long, then you potentially get burn marks and stuff like this. So again, we've got an optimum window where we need to cool that down. Now, you can optimize the cooling system within the tool itself. If you've got key areas or delicate areas within a part that needs to be cooled quicker than others, then you need to divert the cooling lines closer to the actual part itself, or move them away depending on what the aspect is needs to be cooled. So heating and cooling is a key thing. We talked about gates. Now, there are various different styles of gates for different applications. I remember as a kid, I used to get the Airfix models, all these little airplane model kits in plastic format in one big sheet. You used to break them off, great, but if you look at that, as you break them off, you still got a little witness mark on the actual plastic component itself. Back then, I didn't understand it, but now it's a fairly critical aspect with respect to gate size and gate type. Now, we've got one particular component we're manufacturing at the moment. Is a very small component, and the that the gate needs to be as minimal as possible. The gate mark needs to be as minimal as possible. And our sort of designers have come up with a very fine, flat fan style, but it's a submarine gate. So it's a combination of and a submarine gate. Really, really good technology. And again, that is leaving us a virtually zero witness mark when that part is broken off of the sprue.
Right. Because just to clarify, the molten plastic polymer is injected through some kind of hole into the mold, right? And at one point, well, the plastic is in the mold, it cools down, the thermoplastic, cools down, solidifies, and then it's that, how to say, sort of the plastic that's in the pipe is still there, and it's got to be cut or broken, right? And then in a lot of cases, the mold opens and then the part is ejected. So there's two aesthetic considerations here. Is in that kind of pipe where there was plastic that's broken, is it going to be very visible? And is that a problem? On some products, it's not a problem at all. On some other products, it's something that actually gives a lot of work to the plastic shop, right? And then the other one is, as I mentioned, the ejection pins are going to push right out of the cavity, and that's why you want. Usually, if a part has one side that has to be aesthetically nice, and the other one, let's say it's not that important that it's nice, then the ejector pins, then that's the part that's like on the cavity side, and then the ejector pins are going to push. It might leave a little bit of a mark when it pushes because the plastic is mostly solidified, but it's not necessarily very, very hard. So there might be a little bit of a mark here. So there's a lot of little things that go into making plastic parts that really look nice, right?
Yeah, indeed, and staying with the injection, that was going to be my last point, but which was a good point. Yeah, you're talking about the aesthetic side of a product. Potentially, that could be the inside or the outside. So the outside is customer facing, the inside is the part that goes together. So that is the obvious place to eject from. So where you've got the pins pushing the components out of the mold tool itself, you would make sure that they are on the non-visible side or the non-critical side. But when it comes to injection, that again, there's an awful lot to think about when we're doing this. Everything needs to be smooth. Everything needs to come out all in one go. Otherwise, you're going to push one side and not the other. It's going to drag or pull and potentially distort the not fully cured or cooled down. So it's still a little bit warm as it comes out of the tool. And you could actually damage some components that way. And we talked about texture earlier. Now, you can imagine a fairly rough texture on one of the surfaces of your plastic part. As we're ejecting that out, we're pushing the component out of a steel tool. We need to make sure that any texture remains intact and in a perfect condition. So we need to make sure that we've got no drag marks or scores or any defective aspects coming in because it's being pushed out during that ejection phase. So we need to make sure that one, we've got clear visibility of the texture as it comes out, and that can be increasing the draft angle. In other words, it's like your sandcastle bucket. You got a fairly steep draft angle there, and you can lift the bucket off of the sand easily. This is what we're talking about, draft angle. So the coarser your texture, the greater the draft angle needs to be. So another consideration to look at there.
Right. Yeah, making sure that the part can be ejected without damages, without scratch marks. Yeah.
Great. And going the other way, if something's really highly polished, it may stick to the tool itself. So again, this is something we need to look at. So the texture and super smooth surfaces are sometimes a little bit difficult and careful when managing. There are certainly ways around it, which is why we're optimizing and running the pilot run in order to optimize the process itself. making sure that we can deliver a reliable product to the customer.
Right, right, right. So you give a good list of the considerations about the mold itself. Yeah.
I think we covered the mold tool itself. So it's probably a good transition point to start to have a look at the injection mold press
Hmm.
optimization now.
Right, right. So there's a few key parameters, right? And then when it comes to the press, the injection molding machine, basically, that keeps the polymer hot and clamps the tool together, clamps the mold shut, and injects the polymer under very high pressure into the mold, and then releases the clamp after a while, right? So what are the key parameters when setting up that machine?
Well, we can cover these in a fairly high level aspect without
Hmm.
going into too much detail because we don't want to be here for hours. But yeah, basically you covered the steps there, and I just want to touch on the tonnage. Everybody talks about, it's like what tonnage machine do we need,
Mm-hmm.
and that refers to the clamp force, basic. So if someone says, oh yeah, that part needs a 90-ton machine, that's all about the clamp force required in order to hold the two halves of the tool together in order to ensure that the pressure required to fill the cavity, core and cavity, is correct. So let's get that one out of the way. So we're talking about pressure, injection pressure. Obviously, if you know anything about injection molding, which one would assume that you do listening to this, is that you got your dried pellets coming in from the polymer or your polymer sort of selected polymer, and that drops into your heater and goes through the screw and the barrel, and all of that is being heated as we're going along, and it's being plasticized through the screw design itself, and then the actual system goes to work once the cycle starts. Now, the cycle starts by the tool closing, or the machine closing the two halves of the tool, clamping those together, like you mentioned. And then we need to look at optimizing the injection pressure. Now, it's all about optimizing the fill of the core and the cavity. Okay, too much pressure, then potentially we're going to get too much material into the core and cavity, and we've got a lot of flash, or we're getting some poor results from solidification. Not enough pressure means that we're getting short shots. Now, a short shot is, you can imagine, you take the sort of the part out of the core and cavity, out of the tool itself, and you've got an incomplete molded part. That's a short shot. In other words, your polymer hasn't filled the core and the cavity of the component in the tool itself. So again, we've got some optimization we need to do here. We need to we've got an operating window with respect to what that pressure is. We need to make sure that we are, one, not getting flash, and two, we're getting the complete molded cavities filled. So that's your injection pressure.
Right. Mm-hmm. Yeah.
Okay.
What are the other
Yeah.
the other parameters?
I shall carry on a roll. Okay. So with pressure, we talked about temperature. Controlling the temperature throughout the whole system and throughout the whole cycle is a super important aspect. You don't want your polymer starting to solidify until it's completely filled the cavity. If it starts to solidify before that, you again going to get short shots or incomplete molds. Having it too hot, you're going to have burn marks. And this goes hand in hand with having the mold tool itself too hot. So again, a lot of machines these days have a closed loop system where it can, continuously feeding back data points. We're talking about temperature. We're going to have various different sensors throughout the whole system, where we're looking at the barrel temperature, we're looking at the tool temperature, we're looking at the material temperature. And that can be optimized and set such that we've got the operating window optimized in order to have the best flowing or fluid polymer running through the system and injected into the mold itself. Okay, so again, various different polymers have different melting points. It's important to understand that, and all of the team within the injection mold crew would understand that and optimize the melting temperature. Say if we're getting incorrect temperature, we're going to get degradation of components, parts. Some of the parts, if they're injected, they may look all right. But like I say, it's solidification issues could give you long-term problems out in the field. In other words, you think it's going to be okay, but because it was molded with the polymer that was too hot, you may have a brittle component where it shouldn't be. So that could be a failure in the field further on down the road. That's another issue. Cycle times is also trying to optimize here throughout the whole system. It's important that any process is optimized from a cycle time, particularly when we're looking at injection molding. Now, the pilot run, let's come back to the pilot run. The reason why we're doing the pilot run, we're on our side of the fence now, don't forget, is to optimize production output and the yields. One, we're making sure the yields are as high as possible. In other words, the product meets specification time and time again. But we're also reducing our cycle time as much as possible. In other words, we're getting as quickly through the injection process as possible, but within the operating window in order to make sure that we are meeting quality standards. So that's a balance. Yeah, that's a balance with respect to material performance, machine performance, tooling optimization, which we talked about, and everything like this.
And I just wanted to mention, if you have suppliers or even within your company or your group, maybe some plastic injection molding operations, it's like everything. If people have strong pressure to cut costs, or maybe to make more, without investing in new machinery or things like that, they might run their machinery a bit too fast. So in the case of plastic injection molding, they might try to optimize things for the fastest, the shortest cycle time. And sometimes they go a little bit overboard with that. And some issues appear that they kind of tolerate, or they close one eye, right? But that's a risk, right? Sometimes it's a temptation, can be a temptation for people. But having said that, as you correctly said, if it's within the operating window, you try to find a point where the cycle time is relatively short, right? And then you set the other parameters the right way so that it all works together nicely for a good result. That is good because everybody wants a lower cost, basically, right? Yeah.
Yeah, exactly. Now, if you look at the cycle time, it's all about cutting corners. Some people cut corners. Now, the cycle time can actually be broken down into logical aspects with respect to trying to optimize each area. So that's we talked about filling the mold. So that's one aspect. We've got the molten polymer going into the mold itself. That's one time stamp, let's say, on the cycle time. Another one is the holding time. Now, it's important that the tool is held together and the pressure, as the screw in the barrel moves forward through the injection, that is held in position. Otherwise, if it's not held in position for a certain period of time, in other words, during the initial cooling stage, if that backs off, we'll potentially get a backflow of molten polymer, causing all sorts of problems.
Right.
So it's important to have that holding time really, really optimized. And this is where a lot of people cut corners. And this is where we see a lot of issues that are not necessarily surface defects, but they're internal structural problems of the actual polymer cooling or not being held under pressure for a period of time. So the holding time is a really important thing. We talked about cooling optimization, and then the part ejection we've already covered. So,
Right.
when we're talking about cycle time, it's not just like, okay, how quickly can this machine run? We've got to break it down and optimize each of those elements within the cycle time itself. And this is why the pilot run
Yeah.
is really important. So
Yeah.
as the holistic view from running an injection mold machine with a tool that has been optimized, it's all about getting the perfect balance with cycle time and a component that meets specification at the end of it.
Right, right. And of course, just one thing to add here in my mind is that might happen one day when, I don't know, it's June in South China, it's hot and humid, and then, when you run production in November, when the humidity is lower, the temperature is lower, obviously the parameters have to be a little bit different, right? There has to be a little bit of training. However, it's very important not to start from scratch. You know the parameters that worked well before, and then you start from that basis, and then you adjust a little bit, right?
Exactly. That's a really important point as well.
Mm.
Once all of the parameters have been set, or at least set within an operating window, everything in life has a tolerance, and that includes exactly what we've been talking about now. Not just the part itself, but the process of actually making the part. And that does change because of the weather, because of the humidity, because of the heat, and everything like this. So it's
Mm.
important to, one, record down all of the settings for each machine and even the operator. Um, Sometimes they can come along and say, I know this machine better than the previous guy. I'm going to make a slight adjustment here, and that could
Right.
have an
A little bit
effect
of
on everything.
tampering. Yeah,
Yeah,
right.
that's right. So, this is my machine, not so, I'm going to dial it up or dial it down as such. So it's really important that a data sheet is put together with all of the parameter settings for, one, not just the actual product itself or the tool number, but two, what machine was that run on last time? Okay, so this lot of settings. Let's keep that continuous, and so we've got some continuity in production. But there will
Mm.
be potential. And as we go forward, it's like if we've got 100,000, a million shots out of a tool, things do change a little bit. Things start to get not quite as tight. So let's say, so you would
Mm.
need
Right.
continuous improvement and optimization as we move forward through the number of cycles a machine does or a tool does.
Yep. Yeah, absolutely. And then it all goes into good process control, right? And
Yep.
there are plastic shops where temperature and humidity are controlled, are a constant all year long. But that is usually for high quality parts that go into high reliability types of products. For example, the German brand Miele, they put a warranty of 20 years on their products. So when they make vacuum
Wow.
cleaners in Dongguan, and I've been in their factory, well, temperature and humidity are controlled. They don't even want that kind of variation. They don't even want to have to do a little bit of trialing and adjustments every time. But that, of course,
Everything is consistent. Yeah.
yeah, of course, the costs, there's an impact on the cost, let's say, right? And that just doesn't really make sense for like general consumer electronics, B2B electronics that do not have to have such a how to say such a high performance, right? So yeah, it's all about process controls, the right process controls for the right context and the right requirements. So I think yeah, I think we're getting to the end of this episode, and basically it's all about getting from you get a nice drawing, then you get into the tooling to make one or 10 good parts, but then you need to go from one or 10 good parts to the ability, the confidence to go into making thousands and tens of thousands of parts, right? And there is really a proven approach to that, and that is what we discussed today. is the pre-production pilot runs and the documentation and all the right setting for the process and the validation, and if necessary, small adjustments on the mold. So thanks a lot, Paul, and that was a very good overview of this rather technical topic. And I hope
great.
I hope that the listeners get some value out of it. And thanks for listening, and you will hear from us next week as usual. Thank you.
Thanks again for listening to this podcast brought to you by the Sofeast Group. We're on a mission to provide you with everything you need to manufacture effectively in Asia, including inspections, auditing, new product development support, contract manufacturing, 3PL warehousing and fulfillment, and much more across Asia's key manufacturing areas. Visit us at sofeast.com, that's SOFEAST.com, to learn more and get help. If you've enjoyed the podcast today, please do rate, review and share, because it will really help others discover us too.